All right, welcome everybody. So in this video, we are going to continue our work with matrices, particularly 2 by 2 matrices that have complex eigenvalues and how we can make sense of the eigenspaces. And ultimately, if there is some analog of diagonalizing these matrices that have complex eigenvalues. Okay, so first we're going to see that these eigenvalues and eigenvectors, they come in pairs. So let's assume that lambda is a complex eigenvalue of a square matrix A, and it has an eigenvector that will denote x. So let's consider what happens when I take A, matrix A, and multiply on the right by the conjugate of the eigenvector x. So I'm going to take A times x bar. And A is a real matrix. So all of the numbers in matrix A are real numbers. So when you take the conjugate of a real number, remember the conjugate does not change the real part, but it does change the sign of the imaginary part. So taking the conjugate of a real number doesn't change it at all. So whether I write A or A conjugate, since A consists of all real numbers, these are equal to each other. So that's all that's happening in this first equation. We're saying that because A is a real matrix, the conjugate of all the entries in A are the same. And now we can use the fact that when we multiply, we take a product of the conjugate of two things, it equals the conjugate of the product. So the conjugate of A times the conjugate of x is equal to the conjugate of A times x. And now we know that lambda is an eigenvalue of A with eigenvector x. So that means ax, by definition, we can rewrite that as lambda x. Because again, what it means for x to be an eigenvector is when we multiply x by A, it operates just the same as multiplying x by lambda. And now we have this product of lambda x that we're conjugating, and we can break that up into the product of two conjugates. So I can write that as lambda conjugate times x conjugate, where now lambda is a complex number and the eigenvector is likely to also be complex. So what we can see from this equation is that we have a non-trivial vector x bar, so that multiplying x bar by the matrix A is equivalent to multiplying x bar by the scalar lambda bar. So this tells me that x bar is an eigenvector for the eigenvalue lambda bar. So lambda bar is an eigenvalue. If lambda is an eigenvalue and the corresponding eigenvector for lambda x bar, if I want to find the eigenvector for the conjugate of lambda, I just conjugate that eigenvector. So there's a lot of complex numbers and conjugates going on here. So just to anchor things in the example that we've been considering, if A is a 2 by 2 matrix with the first column 4, -1 and the second column 5, 2, then we've shown that we have two eigenvalues. Lambda is 3 minus 2i, and lambda is 3 plus 2i. So notice these two eigenvalues come in a conjugate pair. And now what the result above allows me to do is, let's say I want to find the eigenspace, a basis for the eigenspace for each of these complex eigenvalues. Well, I just need to do this once. So I could take the eigenvalue, lambda is 3 minus 2i, and find a basis for that eigenspace, which in this case, one such basis happened to be the vector v, which has real part -1, 1, plus I times imaginary part 2, 0. And if I want to find the eigenspace for the other eigenvalue, which is the conjugate 3 plus 2i, I just need to conjugate this basis. So a basis for the eigenspace for lambda bar equals 3 plus 2i would be, we keep the same real part, -1, 1, as with the previous eigenspace, but now we change the sign of the imaginary part. So we conjugate the eigenspace of lambda to get the eigenspace for the conjugate of lambda.